Hello everyone. Today, we will learn how to use the MCD module for deer transmission simulation through a case model. During this process, we will gain an in-depth understanding of the composition and working principle of the deer transmission system and master how to create rigid bodies, joints, and couplers in the software. Next, we will cover the following topics. Now, let's look at the specific operation. We will start with a demonstration of the specific operation steps. Open the case model, select the application, find the panel of design, choose More, and from the drop-down menu, select Mechatronic Concept Design to enter the MCD module. Once in the MCD module, select the Part Navigator on the left side, then click on Physics Navigator to access the MCD Navigator panel. Before starting the motion simulation, let's first understand the components and working principles of the deer drive simulation system. We can see that the deer drive simulation system consists of pulleys and several meshing gear sets. The working process starts with power input from the pulley, transmitted through the drive axis to gear 1. The power is then transmitted down through the gear mesh, ultimately achieving reciprocating motion via the connecting rod and gear rack. This illustrates the composition and operation of the deer drive system. Based on the previous learning requirements, we analyze which components in this motion system move as a whole. By observation, we know that during operation, the pulley, axis, and this gear act as a single moving unit. Therefore, we click on Rigid Body under the Mechanical, select the three components, pulley, axis, and gear, and create them as Rigid Body 1, naming it Gear 1. Click Apply to complete the creation of the first rigid body. Similarly, we analyze that the power is transmitted from gear 1 to gear 2. The axis and bevel gear, together forming three components, make up a rigid body and move as a single unit. We select these three components, create them as gear 2. Click Apply and complete the creation of gear 2. Next, we select the bevel gear, cylindrical gear, and the axis connecting the two gears as a whole, and create them as gear 3. We then complete the creation of rigid body of the gear 3. Following the same logic, we observe that the gear, along with its axis and connecting attachments, move as a whole during motion. We create them as gear 4. Click Apply and complete the creation. Finally, for a separate gear, we create it along with its connecting axis and rocker as a rigid body. Name it Gear 5. Click Apply and complete the creation of Gear 5. After the creation is complete, we observe that the remaining components include a connecting rod or rack and a linear block. We create the connecting rod as a rigid body. Click Apply and complete the creation of rigid body of the connecting rod. Finally, we select the rack. Create it as a rigid body. Click OK. And complete the creation of the entire rigid body system. After the creation of the rigid body, we choose the rigid body color. We observe whether each entity moves as a single unit during the motion process and, if confirmed, we cancel the display of rigid body color. Next, we set the joints for the created rigid body. We know that in gear motion, the movement of gears is always circular. Therefore, we choose the basic joint and create all the gears as hinge joint. We select gear 1 and create it as a hinge joint, and its axis vector can be selected from its outer surface to obtain its vector and anchor point. Click Apply to complete the creation. Similarly, we click Select Attachment, select Gear 2, then choose its outer surface on the axis. Complete the specification of the axis vector and anchor point, and click Apply to complete the creation of the hinge joint. Following this process, select the outer surface of Gear 3 to complete the specification of the axis vector and anchor point. And click Apply. Next, choose Gear 4, that is, an outer surface on Gear 4. Complete the specification of the axis vector and anchor point. Caution: when creating Gear 3, its vector points outward from the screen. Therefore, to ensure that both values are positive during meshing and calculating the transmission ratio, we can reverse the direction of Gear 4 so that Gear 3 and Gear 4 mesh in opposite directions. Click Apply to complete the creation of the hinge joint for Gear 4. Next, we create the hinge joint for Gear 5. Click on Select Attachment, choose Gear 5. Set its outer surface as the axis vector and anchor point. Click Apply, and complete the creation of the hinge joint for Gear 5. After completing this, let's look at the connecting rod. There are 2 points where the connecting rod connects to the gear axis. We choose the first connector as the connecting rod, with the base from Gear 4 inputting power. Select Gear 4, specify its vector. Choose an inner surface of the connecting rod. Click Apply, and complete the creation of the hinge joint for one end of the connecting rod. Next, we create the hinge joint between the connecting rod and the rack. For the attachment, we select rack, and for the base, we choose connecting rod. Specify the axis vector by selecting an inner surface of the connecting rod, click OK, and complete the creation of the hinge joint. Finally, we need to create a sliding joint for the rack. Choose the basic joint, select sliding joint, and for the attachment, choose the rack. Specify the axis vector to the right, click OK, and complete the creation of the sliding joint for the rack. Thus completing the creation of all joints. After this, we have another step. Since the transmission ratios are different among the meshing gears, it's crucial to create a gear joint. In the mechanical panel under couplers, we select gear. In the gear joint, we choose gear 1 as the master object and gear 2 as the follower object. Next, we set their transmission ratio, which is the inverse of the number of teeth on the gears. Here, the small gear has 15 teeth and the large gear has 22 teeth. Thus, the transmission ratio is the inverse of the number of teeth. We input the number of teeth for the large gear as the primary value and the number of teeth for the small gear as the secondary value. Click Apply, and complete the setting of the transmission ratio for the first gear pair. Similarly, we select gear 2 as the master object and gear 3 as the follower object. The transmission ratio between gear 2 and gear 3 is the inverse of the number of teeth. Here, the large gear, gear 2, has 30 teeth and the small gear has 20 teeth. Therefore, we input the number of teeth for the small gear as the master multiple and the number of teeth for the large gear as the follower multiple. Click Apply, and complete the setting of the transmission ratio. Next, we set the meshing of the third gear pair by selecting gear 3 as the master object and gear 4 as the follower object. The transmission ratio is the inverse of the number of teeth. Here, gear 3 has 20 teeth, and gear 4 has 30 teeth. Therefore, their transmission ratio is 30 to 20. Click Apply to complete the setting of the transmission ratio for the 3 gear pairs. Next, we select rack and pinion for more under mechanical. For the master, we select rack, and for the follower, we select gear 5. The contact point is the numerical distance from the axis of gear 5 to the meshing point between the gear and the rack. By calculation, the meshing distance is 12.5. Click OK to complete the creation of the rack and pinion. At this point, we have completed the creation of the rigid bodies, joints, and couplers for this model. Finally, using position control under speed control, we input a speed for the pulley. We select gear 1 and set its input speed to 90 degrees per second. Click OK to complete the setup of all elements. Next, we click play to observe whether the meshing between the gears matches the real situation. Click play. For the animation, we can see that gears 1 and 2 mesh correctly, and gears 3 and 4 mesh correctly. This motion simulation matches the actual situation, completing the case study of the 6-gear transmission simulation. Today, we learned how to use the MCD module for gear transmission simulation. For this case, we have mastered the composition and working principle of the gear transmission system, as well as the methods for creating rigid bodies, joints, and couplers in the software. I hope everyone can apply the knowledge learned to practical work and improve our design capabilities. Finally, please complete the following homework exercises and practice more after class. This concludes today's lesson. See you next time.